Light leaves Andromeda and spends about 2.5 million years crossing the darkness before it reaches Earth. A spacecraft would have to cross that same distance, while carrying fuel-shielding power navigation, and perhaps life itself, and even at 1/10 the speed of light, the journey would still take roughly 25 million years. The faster the ship moves, the more dangerous dust radiation energy demands and braking become. If calm journeys through questions like this are worth returning to a like subscription or share helps. Calm Space Science continue creating thoughtful explorations of the universe. Thank you for spending part of your time here, and wherever this finds you, leave a comment with the city or country you're watching or listening from, what time it is there, and whether this is part of a quiet evening, a study session, or the final moments before sleep. Ahead lies a voyage where distance itself becomes the most unforgiving environment of all. Andromeda is close only by the standards of galaxies. In the night sky, it appears as a faint patch of light known as Messier 31, yet that small appearance conceals the scale of the first obstacle to any imagined voyage toward it. The galaxy lies about 2.5 million light-years from Earth. A light-year is not a measure of time, but of distance. The span light crosses in 1 year, and even that unit has to be repeated millions of times before it can describe the separation between the Milky Way and Andromeda. Within the local group, the collection of galaxies to which the Milky Way also belongs, Andromeda is one of the largest members. In that limited cosmic neighborhood, it counts as nearby. For a human journey, however, nearby becomes a word with almost no ordinary meaning. The distance is so great that the light entering a telescope from Andromeda tonight began travelling toward Earth roughly 2.5 million years ago. Every visible detail arrives late. The galaxy is observed not as it is at the present moment, but as it was when those photons began crossing the space between the galaxies. That delay is not a flaw in the telescope, and it is not something a more advanced detector can remove. It is built into the distance itself. To see farther into space is also to receive older information, because light requires time to travel. Andromeda therefore presents a peculiar kind of destination. It is clearly visible, carefully observed, and familiar enough to have a name used far beyond astronomy, yet the version available to observation is ancient. Earth does not receive a live view of it. The sky carries a delayed record. The contrast is easy to miss because human vision makes distant objects feel immediate. Light from a nearby room, a mountain, or even objects within the solar system reaches an observer quickly enough that ordinary experience offers little sense of delay. With Andromeda, the delay becomes one of the defining facts. Looking at the galaxy means looking across an interval comparable not to a human lifetime or a civilization, but to a vast span of natural history. The light arriving now left long before any modern observer could have existed to receive it. The journey of those photons continued while generations of life appeared and vanished on Earth, while landscapes changed, and while the human story remained far in the future. Only after all of that time does the light finally reach a telescope or the unaided eye. This makes Andromeda a natural demonstration of how astronomy turns distance into history. The galaxy does not merely occupy another place. It is known through information that has spent millions of years in transit. Any proposal to travel there must begin with that fact, because a spacecraft would have to cross the same physical separation that the light has crossed. The familiar image of Andromeda can make the destination feel almost accessible. It hangs in the same sky as the moon. Planets and stars and no visible boundary announces where ordinary astronomical distances end and the intergalactic scale begins. But the apparent closeness is created by perspective. The moon belongs to the immediate surroundings of Earth. Mars lies within the same planetary system. Even the nearest stars beyond the Sun occupy a vastly smaller scale than the distance to Andromeda. The Milky Way itself is an enormous structure, yet Andromeda lies beyond it, across the space separating major galaxies. The change is not simply from a long trip to a longer trip. It is a change in category. The units that feel generous within the solar system become cumbersome, and even distances measured between nearby stars are no longer enough to convey the gulf. That is why the light year becomes essential. It joins distance to the one traveller capable of making the scale intuitive light itself. Yet even light moving at the local speed limit described by relativity needs about 2.5 million years. Nothing about the visible appearance of Andromeda communicates that waiting time directly. A photograph can fit the galaxy on a screen. A telescope can frame it in a field of view. A chart can place the Milky Way and Andromeda within the same local group. Each representation compresses space until the relationship can be understood. The physical universe does not perform that compression. Between the two galaxies lies the full separation, and any material traveller would have to deal with every part of it. This distinction between map distance and travel distance is the beginning of the difficulty. A line drawn between 2 points has no duration. A spacecraft following that line does. Andromeda also carries a second complication. The destination is not being observed in its current state. If a mission were planned from the light received on Earth, the information guiding the plan would already be millions of years old. The galaxy remains Andromeda, but the exact state being observed belongs to the past. Over millions of years, stars move and galactic environments change. The target must therefore be understood as something evolving rather than as a fixed picture suspended at the end of space. Later problems of navigation become inseparable from this delay, because travelling toward a distant object means predicting where its relevant structures will be, rather than aiming blindly at where their old light appears to place them. Even before the spacecraft moves, time has entered the route. There is a symmetry to the situation that makes the separation feel even more severe. Light travelling from Andromeda toward Earth requires millions of years, and light or a radio signal sent from Earth toward Andromeda would face the same basic crossing time. Information cannot simply bridge the gap at will. The two galaxies may share the local group, but knowledge between them moves at the speed allowed by physics, not at the speed of intention. A message started on Earth would continue through space while an immense interval passed at its point of origin. If an answer were somehow sent back immediately after reception, the total exchange would occupy roughly 5 million years from the perspective of Earth. That consequence belongs more fully to the problem of communication, but it already reveals what the distance means. Andromeda is not only remote from human reach, it is remote from human conversation. No decision made during an ordinary lifetime could wait for a reply. No mission control could operate across the gap in the familiar way. The destination is visible, but interaction with it would unfold on timescales that dissolve ordinary expectations about cause and response. This is why Andromeda is such a powerful starting point for an intergalactic journey. It is not chosen because it is the farthest object that can be imagined. It is chosen because, among the great galaxies beyond the Milky Way, it is comparatively close. The challenge begins with a nearby giant. If the nearest large galactic destination already demands that light spend millions of years in transit, then the scale of the wider universe becomes almost unnecessary to invoke. The local example is enough. The frightening quality of the journey is not created by darkness, emptiness, or any speculative danger waiting between galaxies. It begins with a measured distance and a simple observation. The faint light of Andromeda has already completed the journey that any spacecraft would have to attempt, and it did so at a speed no massive vessel can reach. By the time that light arrives, the world from which it departed belongs to a remote past. The first step toward understanding a voyage to Andromeda is therefore not imagining an engine. It is allowing 2.5 million light-years to remain what they are, a separation so large that even the fastest signal permitted by known physics turns the route into deep time. The distance to Andromeda becomes difficult to understand long before any spacecraft enters the problem. Human intuition was shaped for landscapes measured in steps, journeys measured in days and horizons that can be crossed within a lifetime. Even the solar system already pushes against that scale, but the gap between major galaxies leaves it behind almost completely. A light year is about 9.5 trillion kilometers, and Andromeda lies roughly 2.5 million of those units away. Multiplying one enormous distance by millions produces a number that can be written down, but writing it does not make it easier to feel. The scale becomes clearer only through comparison, and each comparison reveals how quickly familiar astronomical distances collapse into insignificance. The Moon-Earth's nearest large companion is only a little more than 1 light-second away. Light crosses the space between Earth and the Moon in roughly the time of a short pause. Radio messages sent to lunar spacecraft can return quickly enough for human operators to experience the exchange almost as a conversation. Mars is much farther, and the delay changes as Earth and Mars move around the Sun, but even at large separation its distance is still measured in light minutes rather than light years. Communication with a spacecraft near Mars may require many minutes in one direction, enough to prevent immediate control, yet the delay remains recognizable on a human schedule. The nearest star system beyond the Sun changes the scale again. Proxima Centauri lies a little more than 4 light-years away. Suddenly, a radio message is no longer delayed by minutes but by years, and any reply would belong to another stage of a person's life. Even so, Proxima Centauri is almost unimaginably closer than Andromeda. A straight comparison shows the difference with unusual force. The journey to Andromeda is not hundreds of times farther than the journey to the nearest star. It is hundreds of thousands of times farther. What looks like a difficult interstellar crossing becomes a tiny first step when placed beside an intergalactic one. The Milky Way itself provides another useful measure. Its stellar disk spans roughly 100,000 light-years depending on how its boundaries are defined, and even that width is difficult to picture. Light entering one side of the disk would need around 100,000 years to cross to the other. A civilization travelling through its own galaxy at ordinary spacecraft speeds would face timescales that already exceed recorded history by enormous margins. Yet the distance from the Milky Way to Andromeda is around 24 times the approximate diameter of the Milky Way's bright stellar disk. The destination, therefore, does not sit just beyond the edge of the home galaxy in any practical sense. Between the two major spirals lies a separation large enough to contain the scale of the Milky Way again and again. Maps of the local group often make this geometry look manageable, because they compress millions of light-years into a page or screen. The Milky Way appears on one side, Andromeda on the other, and a scattering of smaller galaxies and dwarf companions fill the region between them. On such a map, the crossing may look like a line. Physically, that line is a distance so large that the entire history of human civilization occupies almost no meaningful fraction of the time required for light to traverse it. The difficulty is not only the size of the number, but the absence of any everyday equivalent. There is no terrestrial journey that can be scaled up without breaking intuition. Walking around Earth, crossing an ocean, or travelling to another planet may offer a sense of effort, but the relationship between those journeys and an intergalactic crossing is too extreme for ordinary analogy to remain useful. A more revealing comparison comes from shrinking the universe instead. If the solar system were reduced until the orbit of Earth around the Sun could fit comfortably inside a small room, the nearest stars would still lie far beyond that room, and Andromeda would be displaced to a scale that no single building could contain. Every useful model has to compress the distances so aggressively that the objects themselves become almost too small to represent. This is a general problem in astronomy. Stars and galaxies are large, but the empty regions between them are larger still. The universe is not simply crowded with enormous objects. It is structured by enormous separations. Within the Milky Way, stars are usually separated by several light years, yet they remain bound within the same galactic system. Between major galaxies, the gaps expand to hundreds of thousands or millions of light years. Andromeda is therefore close in the language of cosmology, because many other galaxies lie tens of millions, hundreds of millions, or billions of light years away. The word close describes a relationship between galaxies, not a practical travel distance. This difference between astronomical closeness and technological accessibility is one of the central traps in thinking about spaceflight. A nearby galaxy can still be so distant that every transportation method known to humanity becomes irrelevant by many orders of magnitude. Even the fastest human-made objects move slowly when measured against a light year. Their progress is impressive within a planetary system, but across interstellar and intergalactic scales, the same speeds almost disappear. Distance dominates before engineering can even begin to respond. The Andromeda problem is therefore not created by choosing an absurdly distant target. It appears at the first great galactic neighbour. That is what gives the number its quiet severity. 2.5 million light-years is not a dramatic estimate selected to make space sound larger than it is. It is the measured scale of a galaxy visible from Earth under dark skies. The light collected from that faint smudge has crossed a gulf so extensive that almost every familiar marker of time becomes too short to serve as a useful reference. The rise and fall of cities, the spread of languages, the development of agriculture, and even the existence of Homo sapiens occupy only a small portion of that crossing time. The comparison can be widened further into natural history. Over a few million years, species emerge and disappear. Climates shift, coastlines move, and landscapes are repeatedly rebuilt by erosion and tectonic change. These processes feel slow when considered from the perspective of a human life, yet they become relevant when the travel time of light itself reaches millions of years. Intergalactic distance converts astronomy into a form of deep time. The separation between two places becomes large enough to be compared with evolutionary and geological change. This is why saying that Andromeda lies 2.5 million light-years away carries more meaning than a simple conversion into kilometers. Kilometers preserve distance but hide the role of time. Light-years reveal that even a signal moving at the fastest, locally permitted speed still requires a duration comparable to major chapters of Earth's biological history. No engine design has yet entered the discussion, and already the route has acquired a timescale beyond ordinary civilization. That is the first major constraint. Before fuel shielding, navigation, or survival are considered, the geometry alone has established the problem. Any real journey must somehow cross a distance that light itself treats as a multi-million-year passage. Every slower traveller must either accept an even longer external duration, or invoke relativistic effects by moving extraordinarily close to the speed of light. The distance is therefore not passive background. It dictates the entire shape of the mission. It determines communication delays, energy demands, navigation requirements, and the degree to which the destination changes while the traveller is still in motion. Once Andromeda is measured against the Moon, Mars Proxima Centauri, and the Milky Way, the progression becomes clear. Each step outward does not merely add another stretch of space, it changes the scale on which time, technology, and survival have to be considered. By the time the comparison reaches another major galaxy, the numbers no longer describe a long voyage in the ordinary sense. They describe a crossing through an interval so large that distance itself has become the dominant physical environment. The speed of light introduces a different kind of boundary to the journey toward Andromeda. Distance alone makes the galaxy remote, but relativity determines how quickly any signal can cross that distance. In empty space, light travels at about 300,000 kilometers per second, and within the framework of special relativity, that speed acts as a local limit for the transmission of matter, energy, and information. The number sounds almost unlimited when compared with any machine humanity has built. Light can circle Earth several times in a single second. It can cross the distance from Earth to the Moon in a little more than 1 second and reach the Sun in a little over 8 minutes. Across the solar system, even the longest light travel times are measured in hours rather than centuries. The scale changes completely at Andromeda. A beam of light leaving the vicinity of Earth would need about 2.5 million years to reach the galaxy. The fastest messenger allowed by known physics still turns the trip into an interval comparable to deep biological history on Earth. That fact quietly removes one of the most familiar tools of exploration: rapid communication. Space missions within the solar system already experience delay. Commands sent to distant probes cannot be answered instantly, so spacecraft must operate with some degree of autonomy. Yet those delays remain short enough for mission teams to receive data, study a problem, prepare new instructions, and continue the mission. At Andromeda, that structure disappears. A radio signal transmitted toward the galaxy would travel at the speed of light just as visible light does, and it would still require roughly 2.5 million years before arriving. If a receiver in Andromeda could immediately send a reply, the return signal would require another 2.5 million years. A single exchange would therefore span about 5 million years from the perspective of Earth. No institution, government, language, or known civilization has endured on anything close to such a timescale. Communication would stop being a conversation and become something more like an archaeological handoff between distant eras. The sender and the receiver would not merely be separated by space, they would be separated by the passage of immense stretches of history at both ends. This is not a consequence of weak transmitters or inadequate antennas. Greater power might improve detectability, and larger instruments might recover fainter signals, but no engineering refinement can make the information itself outrun light in ordinary space. The delay is built into the geometry of space-time as described by relativity. That makes the Andromeda problem fundamentally different from a difficult expedition on Earth. On Earth, even a dangerous mission usually remains connected to a wider society through communication. Advice, updated maps, medical information, and strategic decisions can arrive from elsewhere. Across intergalactic distance, such support becomes meaningless for real-time survival. A spacecraft heading toward Andromeda could transmit reports backward, but those reports would need millions of years to reach Earth once the vessel had travelled far enough away. Instructions sent in response would take millions more to catch up, assuming the spacecraft remained in a predictable region, and the communication geometry allowed it. Mission control, as the term is normally understood, would cease to exist. The craft would have to carry its own decision-making capacity, its own scientific judgment, and its own ability to respond to failure. Even before propulsion becomes extreme, the communication delay already forces extraordinary autonomy. The same limit changes navigation. Astronomers determine the positions and motions of distant objects from the light that reaches Earth, but every observation is delayed by the light travel time. For nearby planets, that delay can be calculated and corrected with high precision. For Andromeda, the information is millions of years old. A route toward the galaxy cannot simply aim at the image visible in the sky, as though that image were a current location. The galaxy and the Milky Way continue to move under gravity while their light is in transit. Stars inside Andromeda follow their own orbits. Gas clouds change. Stellar populations evolve. Any real mission would have to predict where relevant parts of the galaxy would be when the spacecraft arrived, not merely where their old light appears to place them. The speed of light therefore sets both the communication delay and the age of the information used to plan the crossing. This becomes especially important when the destination is not a point but a galaxy, more than 100,000 light-years across. Arriving at Andromeda would not mean reaching a single fixed coordinate. A mission would need a specific target within a vast evolving stellar system, and every correction would depend on observations that themselves arrive late. The deeper difficulty is that increasing the speed of the spacecraft does not remove the outside universe from the problem. At ordinary speeds, travel time can be estimated by dividing distance by velocity. At 1% of the speed of light ignoring acceleration and changes in the separation between the galaxies, the crossing would still take roughly 250 million years in an Earth-like reference frame. At 1/10 of the speed of light, it would take roughly 25 million years. These speeds are fantastically beyond present crude transportation, yet the journey remains measured in millions of years. Only when velocity approaches the speed of light very closely do relativistic effects begin to change the time experienced aboard the craft in a dramatic way. Even then, light itself retains the decisive role. No massive spacecraft can be accelerated to exactly the speed of light, according to special relativity, because the energy required increases without bound as that limit is approached. Light does not provide a target velocity that can simply be reached with a sufficiently large engine. It marks a boundary that massive objects can approach but not attain. This distinction matters because the phrase near the speed of light can conceal enormous differences. A spacecraft traveling at 90% of light speed is moving far beyond any current technology, but it still requires millions of years to cross 2.5 million light years, according to clocks approximately at rest with Earth and Andromeda. Push the velocity closer to light speed, and the external travel time approaches the light travel time, but it never becomes less than that through ordinary motion in space. From the outside perspective, a voyage cannot beat the photons already making the same crossing. The travellers may experience time differently because of relativity, but Earth does not. That difference becomes central later because it creates the strange possibility that a journey can be shorter for those aboard while remaining unimaginably long for the galaxy they left behind. Communication becomes even more disconnected under those conditions. Signals transmitted from a rapidly moving spacecraft are affected by its motion, and the changing geometry alters when information can be exchanged. But none of those effects restore anything resembling immediate contact. The vessel remains embedded in a universe where causal influence propagates at finite speed. Every message becomes part of the mission trajectory rather than an instant connection to home. There is also a philosophical weight hidden inside this physical limit, though it requires no speculation to state the underlying fact. Human exploration has always depended on the possibility of return report or response within a recognizable continuity of generations. Andromeda breaks that pattern. A signal can leave Earth carrying information about a particular civilization culture, and scientific moment then arrive after a span long enough for all of those things to have transformed beyond recognition or disappeared entirely. If a reply ever returns the planet receiving, it may bear little resemblance to the world that sent the original message. The communication channel remains physically open, but the social continuity required for conversation may be gone. The speed of light therefore turns intergalactic communication into a record passed through time. It is less like a telephone line, and more like a message sealed into the structure of the universe, travelling faithfully while everything around its endpoints continues to change. This is why 2.5 million light-years cannot be treated as distance alone. The same number simultaneously describes a delay in observational look-back time and a minimum crossing time for information. Every attempt to reach Andromeda inherits all three. The galaxy is far away. Its visible state is old, and any signal sent toward it begins a journey that no sender can personally see completed. Before the problems of fuel shielding or survival appear, relativity has already imposed a quieter constraint. The route to Andromeda is so long that even light cannot preserve ordinary human continuity across it. Present spacecraft reveal the scale of the Andromeda problem more clearly than any futuristic concept because their speeds are real measured, and already among the highest humanity has achieved. Voyager 1, launched in the late 1970s, is now travelling outward through interstellar space at roughly 17 kilometers per second relative to the Sun. That speed is extraordinary by terrestrial standards. It is fast enough to cross an ocean in minutes, and fast enough to leave the planetary region on a trajectory that no conventional aircraft or vehicle could approach. Yet placed against a distance of 2.5 million light-years, the same velocity becomes almost motionless. If a spacecraft maintained a Voyager-like speed in a straight line toward Andromeda, ignoring the changing motion of the galaxies and every practical problem of navigation, it would require on the order of 40 billion years to complete the crossing. The estimate is rough because the exact answer depends on which reference frame and velocity are chosen, but the implication is stable. The travel time would be several times longer than the present age of the universe, which is about 14 billion years. A machine built by a species that has existed for only a tiny fraction of that interval would have to remain functional through timescales longer than cosmic history has so far allowed. This comparison does not show that Voyager is slow. It shows that intergalactic distance is so large that speeds impressive within the solar system become irrelevant across the local group. The problem becomes even sharper when the way spacecraft actually gain speed is considered. Chemical rockets work by throwing mass backward at high velocity. Fuel burns, hot gas expands through an engine, and momentum pushes the vehicle forward. The method has carried people to the Moon, placed probes around distant planets, and accelerated spacecraft onto trajectories that leave the solar system. It is one of the great practical achievements of engineering. But chemical propulsion is limited by the amount of energy stored in chemical bonds and by the speed at which exhaust can be expelled. Those limits are severe when the goal changes from reaching another planet to reaching another galaxy. A rocket must carry propellant, and carrying more propellant increases mass, which in turn demands still more propellant to accelerate that added mass. The relationship quickly becomes punishing. For missions within the solar system, careful staging, gravity assists, and efficient trajectories can manage this difficulty. For a voyage requiring even a modest fraction of light speed, chemical energy is simply too weak. The gap is not a matter of building a somewhat larger launch vehicle. It is a difference of physical regime. Chemical rockets release energies suitable for planetary travel, while relativistic travel requires kinetic energies that rise towards scales associated with nuclear processes and beyond. Gravity assists can increase spacecraft speed without carrying additional fuel by exchanging momentum with moving planets or the Sun, and several famous missions have used them with remarkable success. Voyager itself gained much of its outward speed from encounters with giant planets. But gravity assists depend on the orbital motion and gravitational fields available in a planetary system. They can reshape trajectories and add useful velocity, yet they do not offer a route from tens of kilometers per second to a substantial fraction of the speed of light. The solar system does not contain an endless sequence of planets capable of providing unlimited acceleration. Eventually, the spacecraft leaves the region where such maneuvers are possible and continues with the speed it has acquired. Other present technologies face similar limits. Ion engines can expel propellant much faster than chemical rockets and operate with impressive efficiency for long periods, but their thrust is small. They're excellent for gradual acceleration and precise control over months or years, especially on robotic missions. They do not transform an intergalactic crossing into a human timescale. Solar sails and laser-driven sail concepts offer another path by reducing or eliminating onboard propellant, but current demonstrated systems remain extremely far from anything capable of carrying a large spacecraft toward Andromeda at relativistic speed. The distinction between a probe measured in grams and a vessel capable of protecting complex machinery, biological life, or a closed ecosystem is enormous. Mass enters every part of the propulsion problem. A tiny payload can be accelerated more easily than a city-sized ship, and every layer of shielding, every reserve system, every habitat, and every supply increases the energy that must be delivered. That means the spacecraft most capable of surviving a long journey is also harder to accelerate. Present spaceflight often avoids this conflict because mission durations remain limited enough for lightweight probes to operate with finite fuel, finite electronics, and finite mechanical lifetimes. Andromeda changes the timescale so completely that speed and longevity become inseparable. A Voyager-like mission does not merely need to travel for billions of years, it must remain a spacecraft for billions of years. Its power source must continue working, its electronics must resist radiation damage, its structure must survive impacts and thermal cycles, its navigation system must retain a meaningful target. None of those requirements can be treated as a secondary detail when the journey extends beyond the current age of the universe. Even the idea of simply coasting does not remove the problem. Once a spacecraft reaches cruise speed in deep space, it may need little propulsion to continue moving because there is no atmosphere producing drag. But coasting only preserves whatever speed was achieved earlier. It does not make the destination closer, and it does not prevent components from aging. A vehicle moving at tens of kilometers per second can coast almost indefinitely in principle, yet an intergalactic distance converts that modest success into an impossible schedule for any known engineered system. The universe itself changes while the craft is underway. Stars evolve, galaxies move, the local group is rearranged by gravity. A route calculated at launch would belong to a cosmos that no longer looks the same by the time a slow probe approached its destination. This is one reason ordinary comparisons with ocean voyages are misleading. An ocean vessel crosses a large environment, while the coastline remains essentially fixed on the scale of the journey. A Voyager-speed craft headed toward Andromeda would travel for so long that the destination and the surrounding universe would change substantially before arrival. The mission would not simply endure history, it would outlast entire phases of cosmic evolution. The inadequacy of chemical propulsion therefore appears at several levels at once. Its exhaust velocities are too low for the required cruise speeds. Its fuel requirements become unmanageable as desired velocity rises. The mass of a durable intergalactic spacecraft magnifies the energy problem, and even if a chemical rocket could somehow launch such a craft into deep space, the resulting travel time would make material survival and navigation almost meaningless by present standards. Faster present-day probes do not fundamentally change the conclusion. Some spacecraft reach greater speeds during close approaches to the Sun, where solar gravity accelerates them temporarily to hundreds of kilometers per second. Those achievements are extraordinary, but they occur under specific orbital conditions and do not translate into a sustained outward cruise at that velocity toward another galaxy. Even if a spacecraft could somehow maintain several hundred kilometers per second, for the entire journey, the crossing would still require billions of years. The destination is simply too far for improvements measured by factors of 10 or even 100 to solve the problem. To bring the journey into millions rather than billions of years, velocity must begin to be discussed as a noticeable fraction of light speed. That shift is profound. It means leaving behind the range of speeds where current propulsion feels relevant and entering a domain where energy shielding heat and relativistic effects all become dominant. Present spacecraft are therefore useful not because they suggest a route to Andromeda, but because they establish the baseline from which the true difficulty can be seen. Humanity already knows how to escape planets across the solar system and send machines into interstellar space. Those accomplishments prove that long-distance robotic exploration is possible within a stellar neighborhood. they also reveal with unusual clarity where that capability stops. A probe moving at Voyager-like speed could continue outward for ages, but Andromeda would remain so distant that the age of the universe would pass several times over before the crossing was complete. The problem is not that existing spacecraft need a better fuel tank or a more efficient trajectory. Their entire velocity scale belongs to a different class of journey. To make Andromeda even remotely approachable propulsion would have to move from the realm of planetary engineering into the realm of relativistic physics. 10% of the speed of light changes the Andromeda journey from something longer than cosmic history into something merely geological, and that improvement is still nowhere close to a human voyage. At 1/10 of light speed, a spacecraft would cover roughly 30,000 kilometers every second. That is almost 2,000 times faster than Voyager 1 moves relative to the Sun, far beyond the sustained velocity of any large vehicle humanity has constructed. Yet across a separation of about 2.5 million light-years, even this extraordinary speed leads to a cruise time of roughly 25 million years in a reference frame approximately shared by Earth and Andromeda, ignoring acceleration, deceleration, and the changing motion of the galaxies. The number is revealing because 10% of light speed often sounds close to the relativistic frontier. It is fast enough that ordinary ideas of spacecraft propulsion begin to fail, fast enough for collisions with small particles to become dangerous, and fast enough to demand energies that lie far beyond present missions. But it is still slow compared with the distance itself. 25 million years is not simply longer than a civilization. It reaches far beyond the entire existence of Homo sapiens as a species. Anatomically, modern humans have been present for only a tiny fraction of that interval. A spacecraft departing at this speed would therefore require a travel time tens of millions of years long, while carrying technology created by a species whose entire biological history occupies only a small segment of the route. This places the journey into a timescale normally used for evolution, extinction, tectonic change, and the movement of continents. On Earth, 25 million years can transform ecosystems, reshape coastlines, raise and erode mountains, alter climates, and change the composition of living communities. A spacecraft travelling to Andromeda at 1/10 light speed would have to remain a coherent machine while an interval of comparable magnitude unfolded around its departure world. The difficulty becomes even more severe once acceleration is included. A spacecraft does not begin its journey already moving at 1/10 the speed of light. It must reach that velocity somehow, and a useful mission must eventually slow down again. If acceleration is gentle enough for human occupants, reaching the cruise speed takes time and distance. If acceleration is much stronger, structural loads and biological limits become serious. Either way, the simple estimate of 25 million years represents an idealized lower complexity case in which the vessel somehow acquires the desired speed, coasts almost the entire route, and then deals with arrivals separately. Real flight adds stages, energy losses, course corrections, and the need to carry or receive the means to decelerate. The energy hidden inside the cruise speed is already immense. Kinetic energy rises with the square of a velocity at speeds well below the strongest relativistic effects. So increasing speed by a factor of 100 requires roughly 10,000 times more kinetic energy for the same mass. A spacecraft moving at 1/10 of light speed therefore occupies an energy regime completely different from one moving at the speeds of modern probes. Every kilogram accelerated becomes expensive. Every layer of radiation shielding every habitat, every repair system, every reserve supply, and every structural reinforcement adds mass that must also be accelerated. This creates a deep conflict in intergalactic engineering. The ship needs mass in order to survive, but mass makes the ship harder to accelerate. A lightweight spacecraft is easier to push toward extreme velocity, yet a vehicle intended to remain functional for millions of years would require redundancy protection, power generation, maintenance capability, and perhaps the ability to manufacture replacement parts from raw materials. Each safeguard makes the propulsion problem worse. Fuel presents another difficulty because a conventional rocket must accelerate not only its payload, but also the propellant that will be used later. Carry more fuel, and the starting mass increases. Carry enough fuel to decelerate at Andromeda, and some of that fuel has to be accelerated across intergalactic space, only so that it can eventually be burned to remove velocity. This is one reason advanced concepts often look beyond chemical propulsion, toward fusion antimatter beamed propulsion, or enormous light sails driven by external energy sources. None of these ideas currently provides a practical way to accelerate a large human spacecraft to 1/10 light speed, but they illustrate the scale of the change required. The journey cannot be solved by taking a present rocket and improving it gradually. The propulsion architecture itself has to change. Even if such acceleration became possible, the duration remains unforgiving. 25 million years makes a conventional generation ship almost meaningless. A generation ship is normally imagined as a closed habitat in which many generations are born, live reproduce and die, before descendants eventually reach a distant star. That concept is already demanding for journeys lasting centuries or millennia. Extending it to tens of millions of years introduces a completely different class of biological and social problem. The number of generations becomes enormous. Genetic diversity must be preserved. Ecosystems must remain stable. Cultures, institutions, languages, and technical knowledge must survive through intervals longer than the recorded existence of almost any recognizable human system by many orders of magnitude. A failure that occurs after several million years cannot be addressed by the engineers who built the ship, and there is no reason to assume that the society aboard would remain culturally connected to its point of origin. Over evolutionary timescales, even the biological identity of the travelers could change. Natural selection, genetic drift, deliberate modification, and adaptation to the artificial environment might produce descendants increasingly unlike the population that departed Earth. The mission would no longer resemble a voyage made by a crew. It would resemble a moving world with its own independent history. Machines face a parallel problem. Materials fatigue, radiation alters electronics, seals degrade, lubricants change chemically, microscopic defects accumulate. Even components designed with extraordinary care cannot simply be assumed to survive for millions of years without intervention. A realistic vessel would need the ability to diagnose damage, manufacture replacements, recycle materials, update its own systems, and preserve the knowledge required to do all of this across a span of time longer than the existence of many species. The ship would effectively need an industrial civilization contained within itself, or an automated repair ecology capable of sustaining its own infrastructure. At that point, propulsion is only the first barrier. Longevity becomes a second project of comparable difficulty. Navigation also changes when travel time reaches tens of millions of years. The target galaxy is not fixed. The Milky Way and Andromeda move toward one another's star's orbit within both systems, and the gravitational structure of the local group continues to evolve. A spacecraft launched toward the visible position of Andromeda would be aiming at light that began its journey millions of years ago. Over the following 25 million years, the spacecraft would have to update its trajectory, using progressively newer observations collected as it moved through space. This is possible in principle because the vessel could observe Andromeda directly during the crossing, but those observations would still represent the galaxy, with a delay determined by the remaining distance. The closer the ship moved, the more current the information would become. Navigation would therefore be an evolving prediction rather than a single launch calculation. That adds computational and observational demands to a mission already forced to operate without meaningful real-time assistance from Earth. The strange result is that 1/10 of light speed is simultaneously transformative and inadequate. It is transformative because it reduces the crossing from tens of billions of years at Voyager-like velocity to tens of millions. It is inadequate because 25 million years still erases almost every familiar concept of exploration. There is no ordinary crew lifetime, no continuous mission control, no stable political institution, and no reasonable expectation that the civilization at departure will still exist in recognizable form at arrival. Even if the spacecraft itself succeeds perfectly, the relationship between origin and destination changes simply because time passes. The travelers would not merely leave Earth behind in space, they would leave it behind in history. 10% of light speed therefore marks an important threshold in the Andromeda problem. It is fast enough to expose the brutal energy and engineering demands of relativistic travel, yet slow enough that the journey remains dominated by deep time. Increasing velocity has helped enormously, but it has not restored the mission to a human scale. To do that, the spacecraft would have to move much closer to the speed of light, where another part of physics begins to matter more strongly. At those velocities, the clock carried by the travelers no longer agrees with the clocks left behind, and the journey begins to acquire two very different durations. Relativity changes the Andromeda journey in a way that ordinary speed calculations do not capture, because once a spacecraft moves close enough to the speed of light, time aboard the vessel no longer passes at the same rate as time measured by observers who remain behind. This effect is called time dilation, and it follows directly from special relativity. It does not make the spacecraft exceed the speed of light, and it does not reduce the physical separation between the Milky Way and Andromeda for everyone in the same way. Instead, it changes how different observers divide the journey into distance and time. For a spacecraft moving at a modest fraction of light speed, the effect is small. At 1/10 of light speed, the travelers would experience almost the same duration as observers near Earth, so the journey would still last close to 25 million years. As the velocity rises, however, the disagreement between clocks becomes stronger. A ship travelling at a very high fraction of light speed could cross the distance while its occupants experience far less time than the millions of years recorded in the frame, approximately shared by the two galaxies. This is one of the few known physical effects that can make an intergalactic voyage feel shorter to those aboard, without requiring anything to move through local space faster than light. The distinction is essential, because it can sound as though relativity offers an escape from the distance itself. It does not. From the perspective of Earth, a spacecraft launched toward Andromeda still cannot arrive in less time than light would need to cover the same route through ordinary space. If the galaxies were treated as approximately stationary relative to one another, for a simplified calculation, the external journey time could approach roughly 2.5 million years as the spacecraft speed approached the speed of light, but it could not fall below that light travel time by ordinary propulsion. The travelers may measure something very different because their motion alters their experienced interval. In their frame, the distance along the direction of travel is also shortened through length contraction. This is not an illusion or an error in measurement. It is part of the same relativistic geometry that produces time dilation. The Earth-Andromeda separation as measured by the fast-moving travelers becomes smaller than the distance measured in the frame of the galaxies. The faster the spacecraft moves, the stronger that contraction becomes. This is why the passengers can experience a shorter voyage without breaking the light speed limit. They are not crossing the same measured distance in the same measured time as observers left behind. Different frames assign different values to both, yet this possible relief for the passengers comes at a severe physical cost. The closer a massive object is pushed toward the speed of light, the harder further acceleration becomes. In modern physics, the spacecraft does not simply require a fixed additional amount of energy for every equal increase in velocity. The energy demand grows increasingly steep. Moving from a low speed to a higher one is difficult. Moving from an already relativistic speed to one even closer to light speed is far more demanding. No matter how powerful the engine becomes, a massive spacecraft cannot be accelerated to exactly the speed of light using finite energy. The limit can be approached, but every closer approach becomes more expensive. This turns the attractive side of time dilation into an engineering trap. Significant shortening of the passenger's experienced journey requires velocity so extreme that the energy problem becomes one of the central barriers of the mission. A small relativistic effect is easy to obtain in principle, but not useful enough to solve the timescale. A dramatic relativistic effect is useful to the travelers, but demands extraordinary speed. The mission is therefore forced into the most difficult region of the velocity scale, precisely when relativity begins to offer its greatest benefit. Acceleration adds another layer. A spacecraft cannot instantly jump to near-light speed. It must spend time gaining velocity, and if human beings are aboard, the acceleration must remain within levels their bodies and the ship can tolerate. A gentle, continuous acceleration could make the early phase of the journey feel surprisingly manageable, and relativity would gradually become more important as speed increased. But providing thrust continuously for long periods would require an energy source and propulsion system far beyond present technology. The ship would also need to reverse the process before arrival. Reaching Andromeda at near-light speed without a way to decelerate would not count as arriving in any useful sense. The vessel would pass through the galactic region at enormous velocity, leaving little opportunity to enter orbit around a star or approach a destination safely. Slowing down requires removing roughly the same kinetic energy that was invested in speeding up, unless an external braking mechanism can be used. This means that the voyage has two major energy climbs, one associated with departure and one associated with arrival. Relativistic travel also complicates the meaning of separation from Earth. Suppose the travelers experience a journey dramatically shorter than several million years because their velocity is extremely close to light speed. Their own biological and technological continuity might then become easier to imagine than on a 25 million year voyage. But Earth does not share that shortened duration. Millions of years still pass there. Any civilization that launched the spacecraft would be buried in deep history by the time the vessel approached Andromeda. Continents could shift substantially. Species could emerge and vanish. The sun would continue its motion around the Milky Way. Human culture, if anything descended from it still existed, would almost certainly be unrecognizable. Relativity could preserve the travelers from experiencing the full external duration, but it could not preserve their relationship with the time they left behind. The journey becomes a one-way displacement not only across space but into the future of the outside universe. This difference becomes especially stark when communication is considered. Signals sent from the ship still travel at light speed. Messages to Earth would not restore a shared present. Depending on the spacecraft's motion and position, transmissions would arrive. After enormous delays, and replies would face the same fundamental limit. The occupants might experience years or centuries, while millions of years passed externally, but no ordinary exchange could bridge that difference. The faster the spacecraft moved, the more pronounced the relativistic effects on observed frequencies and timing would also become. Light arriving from ahead would be shifted toward higher energies, while light from behind would be shifted differently because of the relative motion. The external universe would not merely appear to run on another clock. Its radiation field would be transformed by the spacecraft's velocity. That becomes important because the same speed that produces useful time dilation also makes the environment more dangerous. Photons and particles encountered from the forward direction carry greater energy in the spacecraft frame. Sparse gas that seems almost harmless at low velocity becomes a stream of energetic impacts. Dust grains become still more serious. Relativity, therefore, does not isolate the travelers from the problems of space. It intensifies some of them. The faster the mission tries to go in order to shorten experienced time, the greater the demands on shielding navigation, thermal management, and structural protection. This creates another trade-off. At lower speed, the environment is gentler, but the journey lasts far too long. At higher speed, the experience duration improves, but the vehicle is exposed to a more violent version of the space ahead. There is no obvious velocity where all difficulties decline together. Each gain shifts pressure somewhere else. Near light speed travel also makes small errors increasingly important. A course correction performed at relativistic velocity involves enormous momentum, and every maneuver carries an energy cost. The spacecraft cannot assume that a target identified millions of years earlier remains exactly where an old image placed it. It must continue observing Andromeda, refining predictions and planning its arrival into a galaxy that changes while the crossing proceeds. The closer the ship gets, the less outdated its observations become. But the final approach is also the stage when excessive velocity becomes most dangerous. A successful mission would need the precision of deep space navigation, combined with the energy control of a relativistic machine, maintained across a journey whose external duration still belongs to deep time. The strange promise of relativity is therefore real, but narrow. It can change the experience of the travelers. It can make a voyage that lasts millions of years in the galactic frame correspond to a much shorter interval aboard a sufficiently fast spacecraft. What it cannot do is make Andromeda close. In the ordinary sense, allow a massive ship to reach light speed, erase the energy requirement, or keep Earth synchronized with the travelers. The cost of reducing experience time is an increasingly extreme demand for velocity, and the cost of that velocity appears everywhere else in the mission. Relativity does not remove the distance. It rearranges who has to endure its time. The energy problem becomes unavoidable as soon as the spacecraft is treated as a real object rather than a point moving through a calculation. Speed alone does not describe what has to be supplied. A vessel has mass, and giving mass a large velocity means storing an enormous amount of kinetic energy in its motion. At ordinary speeds, that energy can be estimated with familiar formulas, but as the velocity approaches the speed of light, relativity changes the relationship and the required energy rises much more sharply. The important point is not the exact equation. It is the direction of the curve. Each additional step toward light speed becomes more expensive than the one before it, and no finite amount of energy can accelerate a massive spacecraft all the way to the speed of light. This turns every near-light speed mission into an energy project, on a scale that has no counterpart in present spaceflight. The problem begins before the ship leaves its own system. A large intergalactic vessel would need structure shielding, navigation equipment, power systems, sensors, computing repair machinery, and perhaps habitats or biological support. Every one of those systems contributes mass. Every kilogram added for survival must also be accelerated. If the mission is crewed, the vehicle becomes heavier still, because it must protect living organisms from radiation, provide long-term environmental control, and carry enough redundancy that a single failure does not end the voyage. The same design choices that make the spacecraft more survivable make it harder to move. This is one of the central contradictions of relativistic travel. The faster the mission needs to go, the more aggressively. Mass must be reduced while the more dangerous the environment becomes, the more protection the spacecraft needs to carry. Propulsion concepts based on fusion are often discussed because nuclear reactions release far more energy per unit mass than chemical combustion. Fusion powers stars, and controlled fusion on Earth has long been studied as a potential energy source. In principle, a fusion rocket could eject reaction products at much higher speeds than a chemical engine, and therefore reach velocities that ordinary rockets cannot approach. But an intergalactic mission would demand far more than simply achieving fusion. The engine would need to operate with extraordinary efficiency, direct the reaction products for propulsion, manage intense heat carry or collect suitable fuel, and continue functioning through extreme durations. Even then, pushing a large spacecraft toward a substantial fraction of light speed would require a quantity of usable energy so great that the engineering problem moves far beyond current fusion research. Antimatter appears even more powerful, because when matter and antimatter annihilate a large fraction of their mass, can be converted into energy. In an idealized propulsion system, this offers an energy density far beyond chemical fuel and potentially beyond ordinary fusion designs. The difficulty is that antimatter is not a convenient natural fuel waiting to be mined and loaded into tanks. It must be produced, and current production methods require far more energy than the antimatter later releases in a usable form. Only tiny amounts have ever been made, and storing even those quantities requires electromagnetic confinement because contact with normal matter causes annihilation. Scaling that process from microscopic laboratory production to the fuel demands of a massive relativistic spacecraft introduces challenges in manufacturing containment, safety, heat, and conversion efficiency that are difficult even to frame with present technology. Antimatter therefore remains useful as a way to understand what an extreme energy source might look like, but it is not a practical solution to the Andromeda mission. Beamed propulsion attempts to move part of the energy source off the spacecraft entirely. A powerful laser or other directed energy system could push a reflective sail, allowing the vehicle to accelerate without carrying most of its propulsion energy on board. This is attractive because fuel mass is one of the great penalties of rocket travel. A small sail-driven probe might in principle reach an appreciable fraction of light speed if an enormous external beam could remain focused on it for long enough. The challenge becomes much harder as the payload grows. A large spacecraft requires a much larger sail, far more beam power, precise pointing across vast distances, and materials able to survive intense illumination without melting or deforming. The infrastructure at the departure system would itself have to be immense. And once the beam can no longer push effectively, the spacecraft must still solve the problem of slowing down at the destination. Acceleration is only half of the journey. A spacecraft arriving at Andromeda near the speed of light would carry the same enormous kinetic energy that made departure difficult. If it cannot remove that energy, it does not arrive in any useful sense. It simply passes through the region at relativistic velocity. Braking could in principle be achieved with onboard propulsion magnetic interaction sails, or some future external system positioned near the destination. But each option creates another layer of requirements. Carrying braking fuel means accelerating that fuel for the entire voyage. Depending on the propulsion method, the amount can become enormous. Using infrastructure at Andromeda assumes that some system has already reached the galaxy and been built there. Relying on magnetic or photon-based braking requires conditions and technologies that may not provide enough force at the required scale. The energy budget must therefore include not only the cost of reaching cruise speed, but also the cost of surrendering that speed safely. No propulsion system is perfectly efficient. Some energy becomes waste heat, some leaves in forms that do not contribute to thrust, and some must be spent operating the spacecraft itself. At relativistic velocities, even a small inefficiency can represent an extraordinary amount of heat that has to be removed. In space, cooling is not achieved by surrounding air or water carrying heat away. A spacecraft must radiate unwanted energy into space, and radiators have limits set by their temperature and surface area. An engine powerful enough to accelerate a massive intergalactic vessel could therefore face a thermal problem nearly as severe as its fuel problem. The craft must produce tremendous power without destroying itself with the waste energy produced along the way. This is one reason energy cannot be separated from spacecraft architecture. The engine fuel shielding radiators and structural mass all interact. Increasing one requirement makes another harder. Even the source of energy does not solve the question of how that energy is transferred into motion. A civilization might hypothetically possess access to energy far beyond anything available today, yet converting it efficiently into directed thrust, while keeping the vehicle intact remains a separate challenge. Relativistic kinetic energy is not merely a large fuel bill. It is a state in which the spacecraft itself becomes an object carrying destructive amounts of stored motion. Any collision, course correction, or braking maneuver must be understood against that background. The higher the velocity, the more severe the consequences of small encounters become, which means more shielding and better navigation are required, and those additions increase mass again. This creates a loop in which speed demands energy. Energy systems add mass demands more energy. And the dangers created by speed demand further protection. The loop does not prove that relativistic travel is forbidden. Physics allows massive objects to move arbitrarily close to light speed if sufficient energy can be supplied. What the physics reveals is how rapidly practicality disappears as that limit is approached. The Andromeda journey therefore forces an uncomfortable distinction between possibility and capability. A trajectory may be permitted by the equations while remaining inaccessible to any engineering system that can reasonably be imagined from current knowledge. Fusion antimatter and beamed propulsion each illuminate a different part of the problem, but none removes the full chain of requirements. The ship must accelerate, survive the acceleration cruise through space, protect itself at speed, carry or receive enough energy to make corrections, and then decelerate at the far end. Every stage has to work together. The energy barrier is frightening not because there is a single impossible number hidden inside it, but because almost every attempt to reduce the travel time transfers the burden into another physical demand. Speed can shorten the voyage. Relativity can shorten the traveler's experienced time. More advanced propulsion can increase exhaust velocity or move fuel off the ship. Yet the energy stored in a massive craft moving near light speed still has to come from somewhere. And before Andromeda can become a destination, the energy must be controlled twice, once to leave and once again to stop. At relativistic speed, the emptiness between galaxies stops behaving like empty space. The density of matter in interstellar and intergalactic regions is extremely low compared with anything on Earth. But low density is not the same as zero density, and velocity changes the consequences of every encounter. A grain of dust that would be harmless to a slow spacecraft can become a serious threat when the spacecraft closes on it at a substantial fraction of the speed of light. The grain does not need to be moving quickly in the ordinary sense. From the spacecraft's frame, the relative velocity is already enormous. Kinetic energy rises sharply with speed, and at relativistic velocities even tiny masses can deliver concentrated bursts of energy when they strike. The result is one of the strangest reversals in the Andromeda journey. The faster the ship moves in order to reduce travel time, the less forgiving the surrounding medium becomes. Space does not need to contain large rocks or obvious obstacles. It only needs to contain ordinary atoms, microscopic grains and occasional larger particles because the spacecraft supplies most of the relative speed itself. Interstellar space is known to contain thin gas, mainly hydrogen and helium, along with dust grains composed of heavier elements, silicates, carbon-rich material and ice in some environments. The density varies enormously from one region to another. Inside dense clouds, it can become much greater, while large regions are extraordinarily tenuous. Between the Milky Way and Andromeda, matter is even more diffuse on average, but the route would not be perfectly clean. The halos of galaxies extend far beyond their bright stellar disks. Gas surrounds large galaxies in vast thin structures, and the broader local group contains material that does not belong neatly to any single star system. A relativistic ship must therefore treat the entire route as a particle environment, rather than as a vacuum in the everyday meaning of the word. Individual hydrogen atoms are the most common example. At low spacecraft speeds, a collision with one atom is insignificant. At a large fraction of light speed, the same atom enters the spacecraft frame with much higher energy. Instead of behaving like a gentle trace of gas, the forward environment begins to resemble a continuous stream of high-energy particles. Those particles can strike the hull, penetrate materials, produce secondary radiation, damage electronics, and gradually erode exposed surfaces. A single hydrogen atom does not destroy a ship, but the journey to Andromeda involves an enormous distance. Even an extraordinarily thin medium becomes important when the spacecraft sweeps through it for millions of light years. Every meter of frontal area collects more encounters. Every increase in velocity raises the energy involved. The threat is cumulative before it is catastrophic. Dust creates the more dramatic version of the same problem. A microscopic grain contains many orders of magnitude more mass than a single atom. At ordinary velocity, it may leave only a small mark on a surface. At relativistic closing speed, its kinetic energy can be released over a tiny impact region almost instantly. Material at the collision site can vaporize. The grain itself can become a burst of plasma and fragments. A crater can form in shielding, and the impact can launch secondary particles deeper into the structure. A somewhat larger grain becomes more dangerous still. The precise damage depends on its size, composition, velocity, impact angle, and the spacecraft's shielding, but the general relationship is unavoidable. The energy available in a collision grows as the mission becomes faster. This creates a design requirement unlike the shielding used on ordinary spacecraft. Present vehicles already encounter micrometeoroids and orbital debris, and engineers protect critical systems with layered structures that break incoming particles apart and spread their energy before they reach the main pressure vessel. Such methods work because the expected velocities and particle sizes remain within a manageable regime. A relativistic intergalactic craft would need protection against impacts with far greater energy. Simply making the hull thicker may not be enough because thick shielding adds mass, and mass increases the energy required to accelerate the ship. Once again, the demands of survival push directly against the demands of propulsion. Several hypothetical approaches could reduce the risk, but each carries severe limitations. A spacecraft might place thick sacrificial material at its forward end, allowing layers to erode gradually during the journey. It might use widely separated shields so that an incoming grain is disrupted before its fragments reach the central structure. It might carry replaceable shielding and manufacture new layers as old ones are damaged. Magnetic fields could deflect charged particles, although neutral dust grains would not respond in the same way until ionized. Powerful lasers might attempt to detect and vaporize larger particles ahead of the vessel, but detection at near light speed closing rates becomes extremely demanding. The system would need to notice a grain at sufficient distance, determine that it lies on a collision course, deliver enough energy to alter or destroy it, and do all of this before the spacecraft reaches the same point. Even successful vaporization does not make the material disappear. It converts a compact grain into atoms, ions, and plasma that still carry relative momentum and may still strike the ship. The goal would be to spread the impact across a larger region or deflect the material away, not to erase its energy. Navigation therefore becomes inseparable from shielding. Large objects might be detected in advance and avoided through small course corrections, but microscopic dust cannot be mapped individually across millions of light years. A craft would have to assume that some fraction of impacts is unavoidable, and design around them. At extreme velocity, course changes themselves cannot be made casually. The spacecraft carries enormous momentum, and even a slight alteration of trajectory requires force and energy. A route through a particularly dense region could therefore be dangerous in two ways. Crossing, it exposes the ship to more particles, while avoiding it may require expensive maneuvers planned far in advance. The safest path might not be the geometrically shortest path. It could instead be a corridor selected to minimize expected gas and dust density, based on astronomical observations and continuous measurements taken during flight. Those observations would need to remain accurate for timescales far beyond present mission planning. The forward-facing side of the spacecraft would bear most of the burden. Radiation arriving from ahead is also shifted toward higher energies in the spacecraft frame as velocity increases. Ordinary starlight and background photons do not necessarily become the dominant hazard at moderate relativistic speeds, but the general effect adds to the same pattern. Motion changes the environment. The vessel is not merely passing through space faster, it is transforming the energy of what it encounters. Gas becomes radiation-like bombardment. Dust becomes impact plasma. Faint background fields become more energetic from the forward direction. The ship carries its own hazard through its velocity. This is why an apparently simple solution such as increasing speed cannot be considered independently of protective engineering. A slower journey faces terrifying duration. A faster journey faces a more violent medium. There is no obvious point where the distance problem disappears without another problem becoming stronger. The danger is particularly severe for a crewed ship because shielding must protect not only machinery, but living tissue. Thick physical shielding can reduce exposure to many forms of radiation and fragments, but it makes the ship heavier. Active electromagnetic shielding may help with charged particles, but demands power and large field structures. Redundancy can protect electronics, but duplicated systems add more mass. The design repeatedly circles back to the same trade-off. Survival requires material, and material requires energy to accelerate. Speed saves time, and speed makes collision protection harder. Even a robotic probe cannot ignore this relationship. Its electronics may tolerate conditions that humans cannot, and it can be made smaller. But shrinking the vehicle introduces new vulnerabilities. A tiny sail or probe has less mass to accelerate, yet it may have very little shielding available before protective material becomes a significant fraction of the total vehicle. A single damaging impact could disable a critical sensor or communication system. An intergalactic probe therefore needs not only speed but exceptional fault-tolerance distributed systems and the ability to continue functioning after repeated damage. Over a voyage toward Andromeda, the craft might slowly lose surface material experience, radiation-induced changes in its components, and replace parts as shielding degrades. Protection would not be a passive shell installed before launch. It would become an active process maintained throughout the crossing. The surrounding darkness could look almost perfectly clear, and still the spacecraft would be moving into a stream of matter that no eye could see. That is the essential danger of relativistic dust. The threat does not come from a crowded field of visible debris. It comes from the multiplication of tiny mass by extreme relative speed. The voyage turns the most dilute environment into something that must be treated with caution every second of the way. In the Andromeda problem, emptiness is not protection. At sufficient velocity, even emptiness contains enough matter to strike back. Radiation becomes a quieter but more persistent threat than dust, because it does not require a single dramatic collision to damage the spacecraft. High-energy particles are already present throughout space, produced by violent events such as supernova explosions, energetic stellar activity, and processes occurring around compact objects. Some travel through the galaxy, as cosmic rays moving at speeds close to that of light and carrying enough energy to penetrate materials disrupt electronics and damage biological tissue. Within the protection of Earth, the atmosphere and magnetic field remove much of this radiation before it reaches the surface. A spacecraft between galaxies would have no comparable natural shelter. Once it left the dense protective environments of planets and stars, radiation exposure would become part of the background condition of the mission, continuing year after year, across a voyage potentially lasting millions of years in the external frame. For a human crew, the danger begins at the cellular level. High-energy particles passing through tissue can ionize molecules, break chemical bonds, and damage DNA. Cells may repair some of that damage, but the process is imperfect, and repeated exposure increases the risk of cancer tissue degeneration, neurological effects, and other long-term injury. Radiation can also affect reproductive cells, which becomes especially important for any mission that depends on many generations of biological continuity. A single short exposure might be survivable, yet an intergalactic journey creates the harder problem of cumulative dose. Even a low rate of damage becomes significant when it continues across years, centuries, or far longer. The challenge is not merely protecting one crew during one expedition. It is designing an environment in which biological systems can remain healthy through a duration that exceeds every human experience of habitation. Thick shielding can absorb or scatter some incoming particles, and materials rich in hydrogen are useful against certain kinds of radiation because their light nuclei can reduce the energy of charged particles with less production of some dangerous secondary fragments than very heavy shielding materials. Water fuel, stored supplies, and specialized polymers could therefore be arranged around living areas as part of the protective structure. Yet shielding is never free. Every additional layer adds mass, and every kilogram must be accelerated, carried across intergalactic space, and eventually slowed at the destination. The same conflict that appears in dust protection returns here. A lightly built spacecraft is easier to accelerate but harder to protect. A heavily shielded spacecraft may be safer for its occupants but vastly more demanding to propel. Radiation therefore converts biological survival directly into an energy requirement. Active protection has also been proposed in principle. Strong magnetic or electric fields might deflect some charged particles before they reach the hull, creating an artificial protective environment around the vessel. The approach is attractive because it might reduce the amount of physical shielding required, but cosmic radiation contains particles with such high energies that deflecting them significantly could demand very large field strengths, extensive structures, and continuous power. Neutral radiation, such as energetic photons, would not respond to magnetic fields in the same way. No single shielding method removes every threat. A realistic spacecraft would likely need layers of passive material, active systems, protected internal zones, redundant electronics, and continuous monitoring of the radiation environment. Even then, protection would have to remain effective for a period so long that the shielding itself becomes part of the maintenance problem. Radiation damages machines as well as living tissue. Energetic particles can deposit charge inside electronic components, flip stored information, corrupt memory, alter sensor readings, and permanently damage semiconductor structures. Modern spacecraft already use radiation-hardened electronics, error-correcting memory redundancy, and protective shielding, because even missions within the solar system encounter these effects. An Andromeda craft would have to carry these principles to a level far beyond present requirements. It could not assume that a processor cable detector or power controller would remain unchanged for immense periods. Components would fail, materials would slowly accumulate defects, insulation would degrade, sensors would lose sensitivity. The problem would not be preventing every failure, but ensuring that failure never became terminal. That suggests a spacecraft designed less like a finished machine and more like an industrial system able to renew itself. Electronics might be modular and replaceable. Manufacturing systems could produce new parts from stored materials or recycled components. Software would need to detect corrupted hardware, isolate damaged systems, rebuild lost functions, and preserve essential information, even if entire generations of computers were replaced. The ship could not rely on original hardware surviving from departure to arrival. It would need continuity through reconstruction. This requirement becomes even more demanding because no repair team on Earth could intervene. Communication across the growing distance would eventually involve delays measured in enormous spans of time. A malfunction discovered far from the Milky Way could not be described to engineers at home and followed by useful instructions. Any response would arrive far too late to matter. The craft must diagnose the failure, locally understand its significance, choose a remedy, manufacture, or redistribute resources, perform the repair, verify the result, and continue the mission. If biological occupants remain aboard, they would need equivalent independence. Medical systems could not simply consult distant specialists. Environmental failures could not be solved by emergency resupply. The spacecraft would have to contain enough knowledge and capability to function as its own laboratory, hospital, factory, power station, archive, and maintenance facility. Radiation makes this autonomy necessary because it guarantees that damage is not a remote possibility. Across immense durations, some degradation should be expected. The more useful design question becomes how well the vessel can survive repeated damage without losing the capacity to repair itself. Redundancy helps, but redundancy also has limits. Carrying 2 copies of a critical system is useful if one fails. Carrying many copies extends resilience. Yet every spare part adds mass, and a mission lasting millions of years could consume any finite stock of replacements. A more durable strategy would require manufacturing new components from raw materials, recovering usable elements from damaged equipment, and maintaining the machines that perform the manufacturing. That creates a recursive problem. Repair systems themselves must be repairable. Fabrication tools require calibration. Sensors must be replaced. Software archives must remain readable after countless hardware generations. Knowledge must survive migration from one technological platform to another without silent corruption. A tiny error in an archive might be harmless, but repeated copying across vast spans could gradually distort crucial instructions unless strong verification systems preserved them. For a robotic probe, this creates a demand for extraordinary long-term information integrity. For a crewed vessel, cultural transmission becomes entangled with engineering survival, because knowledge of how the ship works would have to persist even if languages, institutions, and social structures changed. Radiation therefore attacks more than components. It attacks continuity. Its effects encourage constant rebuilding, and rebuilding requires a stable chain of information linking each new generation of machinery to the design logic of the systems before it. Power generation must endure the same timescale. Shielding field sensors, computers, life support, manufacturing, navigation, and repair all require energy. A power system designed for decades is not enough. Radioisotope sources decay. Reactor components age. Fuel is consumed. Solar power becomes less useful once the spacecraft travels far from stars unless enormous collectors can capture faint ambient light, or the ship approaches a new stellar system. A long-duration vessel would need an energy architecture capable of renewal, perhaps through stored fuel, advanced nuclear processes, resource collection, or technologies beyond those currently available. Whatever the solution, it must remain reliable without external maintenance. A failure in the main power system could disable radiation protection, thermal control, navigation, and repair simultaneously. The spacecraft therefore needs multiple layers of power redundancy, Yet each layer again increases complexity and mass. The duration of the journey magnifies every small weakness. A component with an extremely low annual failure probability may still be unsuitable when the mission spans geological time. A seal that slowly loses flexibility, a memory cell that occasionally changes state, or a radiation shield that erodes by an almost invisible amount becomes important when multiplied across immense intervals. Engineering normally manages risk by testing components over realistic service lives and replacing them before failure becomes likely. No laboratory can test a machine directly across millions of years. Designers would have to understand degradation mechanisms well enough to predict behavior far beyond any experimental duration, while also accepting that unexpected failure modes would eventually appear. The craft must therefore be prepared not just for known problems, but for uncertainty in the hardware itself. This may be the most demanding aspect of long-duration radiation survival. Protection cannot depend on perfect foresight. It must depend on adaptability. The ship must notice when its own assumptions stop being true. A sensor type may age differently than expected. A shielding material may accumulate damage in an unforeseen way. A manufacturing process may drift after thousands of cycles. The vessel must retain enough diagnostic intelligence to recognize these changes and alter its own systems accordingly. At that point, the line between spacecraft and self-maintaining technological ecosystem begins to blur. The journey to Andromeda no longer asks whether a hull can survive radiation. It asks whether an entire technological lineage can remain coherent under constant exposure, repair itself through repeated damage, preserve its knowledge and continue functioning without meaningful help from the world that launched it. Radiation is dangerous because it never needs to deliver one final blow. Given enough time, even small effects accumulate. The voyage, therefore, demands something more difficult than resistance. It demands renewal. A spacecraft intended to survive for millions of years cannot be designed as a larger version of anything that flies today, because almost every modern machine assumes a finite service, life-periodic maintenance and access to replacement parts. Even the most reliable spacecraft operate on timescales, measured in years or decades, and their survival depends on carefully managed margins that would become meaningless across geological time. A vessel bound for Andromeda at a speed well below the most extreme relativistic regime might remain in transit for millions or tens of millions of years, and that duration changes the definition of engineering. The question is no longer whether a component can last long enough. The question is whether the system can keep rebuilding itself after the original components have disappeared. Materials fatigue, electronics accumulate radiation damage, seals fail, and microscopic cracks grow under repeated stress. Given enough time, almost every passive assumption becomes an active maintenance problem. A long-lived intergalactic vessel would therefore need to treat its own structure as something temporary. Parts would be inspected, removed, recycled, remanufactured, and replaced continuously. Sections of the hull power systems, sensors, and computers might all be replaced many times before arrival. The ship that arrived in Andromeda might contain very little of the material that originally left the Milky Way, yet still preserve a continuous identity through its mission navigation records and self-maintaining architecture. Its survival would depend on renewal rather than permanence. Self-repair, however, is more demanding than carrying spare parts. Any finite store of spares eventually runs out if the mission lasts long enough. A vessel crossing millions of years would need manufacturing capability able to convert raw feedstock into structural members, circuits, optical systems, pumps, valves, cables, shielding, and whatever new components become necessary. It would also need machines capable of repairing the manufacturing machines themselves. This recursive requirement quickly reaches deep into the design. A fabrication unit depends on sensors, actuators, precision tools, software, and power. Each of those systems can fail. The ship, therefore, cannot depend on one irreplaceable machine at the center of its maintenance chain. It would need redundancy, distributed fabrication, stored design information, and enough general-purpose capability to reconstruct critical tools from simpler ones. The goal would be preserving an industrial lineage rather than a finished product. Materials would have to circulate through that lineage. Damaged shielding could be melted and recast. Broken electronics could be stripped for useful elements. Structural components could be reprocessed. Waste streams from biological or mechanical systems might become feedstock for new production. Nothing could be treated casually as disposable because a mission lasting millions of years cannot assume access to fresh supplies. That problem becomes much harder if human beings are aboard. A closed ecological system has to provide air, water, food, and waste recycling while preventing small chemical imbalances from accumulating across generations. On Earth, ecosystems are resilient partly because they are enormous, diverse, and connected to vast reservoirs of atmosphere, oceans, soil, rock, and sunlight. A spacecraft contains only a tiny artificial fraction of that complexity. Essential elements would have to circulate through biological and mechanical loops without gradually becoming unavailable. Microorganisms, crops, pathogens, and human populations would all continue to evolve. Ecological relationships could drift away from their original design. Even if the system remains stable for centuries, that tells little about its behavior across millions of years. Biological stability on such a timescale is not the same as keeping a greenhouse operating for many generations. It is closer to sustaining a small artificial biosphere through evolutionary time. Human populations would also change. A generation ship lasting a few centuries might plausibly preserve social continuity through education institutions and cultural memory. Stretch the voyage to millions of years, and the idea becomes far less stable. Languages transform, beliefs divide, political systems rise and disappear. Knowledge can be lost, reinterpreted, or rejected. A mission purpose established at launch would have to remain meaningful to descendants, separated from the founders by a number of generations too large to imagine as a continuous human community. Even biology would not remain fixed. Natural selection in a closed environment, random genetic changes, deliberate engineering, and changes in reproductive patterns could gradually alter the population. The beings arriving at Andromeda might still descend from humans, but there is no reason to assume that they would remain biologically or culturally identical to the people who began the mission. This makes a conventional generation ship a weak match for the timescale. The ship would not simply transport a society, it would become the environment in which a new branch of history unfolded. The destination could become a tradition rather than a remembered place. For this reason, robotic or largely autonomous probes may be more plausible than human travelers. Machines do not require breathable atmospheres, food webs, medical care, or genetic continuity. They can be made smaller, and reducing mass directly lowers the energy required for acceleration and deceleration. A robotic probe can also tolerate long dormant periods if its systems are designed to wake periodically, assess, damage, recalibrate navigation, and return to a low-power state. Yet the advantage should not be overstated. A machine that must function for millions of years still faces almost impossible demands by present standards. Its memory cannot simply be stored once and forgotten. Radiation can alter data, materials can degrade, clocks can drift, mechanical systems can seize, power sources can decay or exhaust their fuel. The probe would need methods for checking its own information, correcting corruption, and reproducing its critical functions before failures accumulate beyond recovery. That implies a level of autonomy much greater than current spacecraft possess. It would have to distinguish aging from dangerous malfunction, choose repair strategies, test new parts, and redesign subsystems when old solutions stopped working. The software controlling such a probe would have to remain understandable to the machine after countless generations of hardware replacement. As processors and sensors changed, core mission information would need to migrate forward without losing integrity. Error correction could protect stored data, but only if the systems performing the correction remain trustworthy. Multiple independent archives could compare one another. Physical reference standards could help verify measurements. Essential instructions could be stored in several forms so that one failure mode did not erase the mission. The spacecraft would need to preserve not merely data, but the ability to interpret data. That includes physical models, navigation logic, engineering principles, and enough context to reconstruct its records. Long-term survival also requires a source of energy that can be renewed or conserved with extraordinary care. A reactor carrying finite fuel eventually runs down. Radioactive sources decay. Batteries fail. A probe might reduce demand by sleeping through long portions of the voyage, but navigation, collision monitoring, thermal control, and periodic maintenance may still require power. Possible strategies include long-lived nuclear fuel, extreme energy conservation, or future systems able to exploit resources encountered along the route. None of these possibilities is available as a demonstrated solution. They show instead why the survival problem cannot be separated from the energy problem. A self-repairing ship needs power to repair itself. A system that loses power before it can rebuild its power source is finished. Redundancy, therefore, has to exist at the level of energy generation, as well as computing and structure. The most durable design might resemble a network of semi-independent modules, rather than one tightly centralized spacecraft. If one module failed completely, others could preserve the mission. Distributed manufacturing could reduce the chance that one accident destroyed the ability to rebuild. But every additional module increases mass, and mass again increases propulsion demands. The Andromeda journey repeatedly forces the same trade. More resilience requires more material. More material requires more energy. More speed reduces the external journey time but increases impact and shielding demands. Less speed makes the environment gentler but extends the interval through which every system must survive. There is no simple design choice that improves all conditions at once. This is why the question of a million-year spacecraft is more fundamental than the question of a durable hull. No known material could simply be expected to sit unchanged until arrival. The successful vessel would have to remain dynamic, replacing itself faster than time, and damage could erase its functions. For human passengers, that means maintaining an artificial world across evolutionary time. For autonomous machines, it means maintaining a chain of repair, manufacturing, memory, and power across durations that no technology has ever approached. The most realistic traveller to Andromeda may therefore not be a crew sealed inside an immortal ship, but a self-renewing machine whose individual parts are temporary and whose continuity exists in information function and the repeated act of rebuilding itself. The coordinates of Andromeda are not a frozen address waiting at the far end of space. Every observation from Earth is already delayed by roughly 2.5 million years, which means the galaxy seen in telescopes is an ancient version of the destination rather than a current portrait. The stars visible in its spiral structure have moved since the light now arriving at Earth began its journey. Gas clouds have shifted. Some massive stars have completed their lives. New stars have formed. Stellar remnants have cooled. Binaries have changed orbit, and countless local environments have evolved under gravity, radiation, and internal galactic motion. None of this means that Andromeda has become unrecognizable in only a few million years. Galaxies evolve slowly compared with human history. Their overall structures persist across long intervals. But an intergalactic spacecraft would not need only the broad location of the galaxy. it would eventually need a precise destination within it, and that requires understanding the difference between where Andromeda appears to be and where its relevant structures will actually be when the spacecraft arrives. The problem begins with light itself. Astronomers determine the position and motion of distant objects by collecting photons that left them in the past. For nearby stars, the delay is measured in years or decades. For Andromeda, it is measured in millions of years. The apparent position of the galaxy therefore describes a direction to an old signal, not a direct line to a fixed modern target. Even if a spacecraft could depart immediately, its navigation system would have to predict the future evolution of both the Milky Way and Andromeda, while correcting continuously as newer information arrived during the voyage. The strange advantage is that the observations would become less outdated as the spacecraft moved closer. At launch, the light reaching the ship from Andromeda would still represent the galaxy as it was millions of years earlier. Halfway across the gap, the delay would be much smaller. Near arrival, the ship would finally receive a more current view of the destination than anything visible from Earth at the moment of departure. Navigation would therefore improve with proximity, but only if the spacecraft survived long enough to keep observing, recalculating, and adjusting its route. The destination would gradually emerge from history into something closer to the present. That process sounds simple, until the scale of Andromeda itself is considered. A galaxy is not a single object like a planet or spacecraft. It is an enormous gravitational system containing hundreds of billions of stars, diffuse gas dust, dark matter star clusters, stellar remnants, and smaller satellite galaxies. Reaching Andromeda in a broad sense might mean crossing into its extended halo, while reaching a useful target could require entering the interstellar disk approaching a specific star or positioning the spacecraft near a stable region from which detailed exploration could begin. Those goals demand very different trajectories. The apparent center of the galaxy might be easy to identify, but aiming for the center would not necessarily be desirable. The inner regions contain denser stellar populations and more complicated gravitational environments. A scientific mission might instead choose an outer region with lower stellar density and a more gradual approach. A crewed mission, if such a thing were ever possible, might prefer a star system with suitable conditions rather than a location chosen for geometric convenience. Yet any specific star observed from Earth would itself be seen millions of years in the past. A star that appeared stable at departure could have evolved significantly before arrival if it were massive enough, and a planetary system inferred from old data could no longer be in exactly the same state. The longer the spacecraft spends in transit, the greater this mismatch becomes. At 1/10 of light speed, the journey would take roughly 25 million years in the frame associated with the galaxies. The target would then not be merely 2.5 million years older than the image seen at launch. It would be tens of millions of years beyond that image by the time the spacecraft arrived. During such an interval, stars inside Andromeda would continue orbiting through the galaxy. A star does not remain fixed relative to the galactic center. It moves under the combined gravitational influence of the galaxy, and over millions of years that motion can carry it through a substantial portion of its orbit. A target chosen from a static sky map would therefore be useless without a model of its velocity. Astronomers already measure motions using shifts in spectral lines and, where possible, changes in apparent position. For Andromeda, however, determining precise three-dimensional motions of individual stars across such a distance is extremely difficult. The spacecraft would need to refine those estimates during flight using its own instruments. The closer it came, the easier some measurements would become because individual stars and regions could be resolved more precisely and their motions tracked with greater accuracy. The route would gradually shift from intergalactic navigation toward navigation inside a moving galaxy. Andromeda's internal evolution adds another layer. Spiral patterns are not rigid arms made from the same stars forever. Stars enter and leave regions associated with spiral structure as the galaxy evolves. Gas clouds collapse, stars form supernovae, enrich surrounding material, and gravitational interactions alter local conditions. The broad appearance of the galaxy remains recognizable over millions of years. But the detailed arrangement is never static. A mission aimed at a particular nebula star-forming region, or stellar association, would have to expect that the feature might change or disperse before arrival. This distinction matters because distant astronomy often produces images that feel spatially stable. A photograph freezes a galaxy into a single pattern. The physical galaxy is not frozen. It is a system already in motion when the photons depart and still in motion when they are received. Intergalactic travel exposes the difference between image and object. A spacecraft navigating toward Andromeda would not be chasing a picture. It would be intercepting an evolving gravitational structure. The Milky Way itself is also moving during the journey, so the departure point cannot be treated as fixed. The Sun orbits the center of the Milky Way on a timescale of hundreds of millions of years. Over a journey lasting tens of millions of years, the solar system would travel a significant distance through its galactic orbit. The orientation of the departure environment would change, nearby stars would drift into new configurations, and the spacecraft would carry momentum inherited from the motion of the solar system and the Milky Way. Mission planners would therefore need a reference frame appropriate to the local group, rather than imagining Earth and Andromeda as stationary points on a flat map. The trajectory would be a calculated interception between moving systems. Gravity would also influence the crossing. A spacecraft leaving the Milky Way must climb through the gravitational potential of its home galaxy, and then travel through the broader gravitational field of the local group. As it approached Andromeda, the galaxy's gravity would increasingly shape the path, accelerating the spacecraft inward, unless braking or course control compensated. For a slow mission, these effects accumulate over long periods. For a relativistic mission, the crossing is dominated more strongly by the initial velocity, but precise arrival still requires accounting for the changing gravitational environment. Aiming becomes inseparable from slowing down. A ship that predicts the destination correctly but arrives with excessive velocity could pass through the system without any practical chance to remain there. The changing target therefore combines astronomy with propulsion. Navigation is not merely knowing where to point, it is knowing where the destination will be, how fast it will be moving, how the spacecraft's own path will curve, and when braking must begin. The farther into the future the arrival lies, the more the mission depends on prediction followed by continuous correction. This makes autonomy essential once again. Earth cannot supply real-time updates across such distances. The spacecraft would need to observe Andromeda, directly compare new measurements with its internal model, revise the expected positions of potential targets, and choose among them as conditions became clearer. A destination selected at launch might be abandoned millions of years later because a better target emerged. The mission plan would therefore need flexibility built into its purpose. The craft might begin with a general goal of reaching Andromeda and postpone the final choice of star system until the galaxy was close enough for accurate local observations. That strategy reduces the risk of trusting ancient data too literally. It also changes the meaning of exploration. The mission would depart with incomplete knowledge, by necessity carrying not a perfect map, but the ability to construct a better map as it moved. In that sense, the final approach to Andromeda would be the first time the travellers or probe could observe the galaxy with information close enough to the arrival epoch to guide precise decisions. The old image from Earth would slowly be replaced by newer light collected along the route. What began as a destination known through a multi-million-year delay would become progressively more current as the remaining distance collapsed. Yet this does not make the journey easier. It reveals that the voyage is aimed not only across space but across changing time. The spacecraft must reach a galaxy that continues evolving while it travels, and success depends on predicting enough of that evolution to meet a moving target rather than an ancient image. The separation between the Milky Way and Andromeda is already changing. These two galaxies are not fixed islands suspended at permanent coordinates, and the roughly 2.5 million light-years between them is only a present measurement inside a much longer gravitational story. Andromeda has motion toward the Milky Way, and over immense spans of time the two large galaxies are expected to interact strongly. That fact changes the meaning of the journey. The distance that appears so overwhelming today is not a wall placed permanently between two systems. It is one stage in the changing structure of the local group, a structure in which galaxies move smaller companions' orbit and gravity acts continuously or across scales that are difficult to notice within a human lifetime. On ordinary timescales, the separation feels constant because the change is far too slow to perceive directly. On billion-year timescales, that assumption breaks down. The galaxies are part of the same gravitational environment, and their relative motion gradually alters both the distance between them and the geometry of the region a spacecraft would have to cross. This does not make a present-day voyage easy. The gap remains about 2.5 million light-years, and no current propulsion system can take practical advantage of the galaxy's approach. But it reveals something important about intergalactic travel. The map itself evolves while the journey is being imagined. The local group is not a static collection arranged like objects on a shelf. The Milky Way, Andromeda, their satellite galaxies and other smaller members all move under the influence of gravity. Some motions are dominated by close companions. Others reflect the larger gravitational structure of the group. The result is a slow rearrangement that becomes significant only when enough time is allowed to pass. For a mission lasting millions of years, even modest changes matter. For the future of the galaxies themselves, the relevant interval becomes billions of years, and the transformation becomes much more dramatic. A spacecraft departing during one stage of this evolution would not be travelling through the same configuration that existed long before launch, and it would not arrive into a system frozen in the state visible from Earth today. The destination and the space between are both participants in the same long motion. Andromeda's approach also exposes the difference between radial motion and the full path of a galaxy. From Earth, astronomers can measure that Andromeda has a component of motion toward the Milky Way. But a galaxy does not simply move along a perfect straight line like a projectile aimed at a target. Its eventual path depends on the combined three-dimensional motion of both systems and on the gravitational influence of the matter distributed through and around them. The stars, gas, dark matter, and satellite galaxies associated with each major galaxy all contribute to the encounter. This makes the future interaction a problem of dynamics rather than simple closing speed. The two galaxies approach. Gravity strengthens the influence they exert on one another, and their structures respond long before any notion of a clean collision between two solid objects would apply. That distinction matters because galaxies are mostly empty space. When two large galaxies interact, the event is not like two planets striking one another surface against surface. Their stars are separated by enormous distances, so direct, stellar collisions are not expected to dominate the encounter. Instead, gravity reshapes the galaxies on a vast scale. Stellar orbits can be altered. Long streams of stars may be pulled outward. Gas can be compressed or redistributed. Satellite systems can be disturbed. The recognizable spiral patterns that define the Milky Way and Andromeda today may not survive unchanged. The interaction is therefore destructive in the sense of reorganizing structure, but not because every star crashes into another star. It is a transformation of orbits, shapes, and large-scale gravitational order. For a hypothetical traveler, this future motion creates an unusual contrast. A spacecraft launched now faces an immense gulf because the galaxies remain widely separated. A spacecraft launched in a far more distant era could begin from a local group with a very different geometry. The distance between the major galaxies could be smaller, and eventually the distinction between travelling from one galaxy to the other may itself become less clear as their structures overlap and reorganize. This does not provide a practical strategy for present civilization, because waiting for galactic evolution requires timescales measured in billions of years. Yet it shows that the difficulty of the Andromeda journey is partly tied to when the journey is attempted. Space is not merely a fixed stage on which technology improves. The astronomical environment also changes. That changing environment would affect navigation in ways that become increasingly important for very long missions. A probe moving slowly enough to require millions or tens of millions of years would have to account for the continuing relative motion of the two galaxies. The route could not be based on a single straight-line measurement taken at departure. Instead, the spacecraft would need to model the evolving gravitational geometry, continue observing Andromeda, and update its expected arrival region. As the galaxies move, the point of interception changes. As the ship enters the gravitational influence of Andromeda more strongly, its own trajectory changes as well. A mission designed without continuous correction could arrive far from its intended region, especially if the crossing time were long enough for substantial galactic motion to accumulate. The same problem becomes even more complicated when the destination is defined as a particular star or planetary system rather than the galaxy in general. Stars inside Andromeda are themselves moving through the galactic gravitational field. Over millions of years, a target star can travel a great distance along its orbit. The galaxy's overall motion toward the Milky Way is therefore only the broadest layer of the navigation problem. The spacecraft must account for the motion of Andromeda as a whole, the internal motion of its chosen destination, and the evolution of the route across the local group. What looks like a simple line between 2 points becomes a prediction involving several nested systems all changing at once. The future interaction between the Milky Way and Andromeda also reminds us that galactic boundaries are less absolute than they appear in photographs. The bright stellar disks are only the most visible parts of much larger structures. Extended halos reach far beyond the regions where most stars are seen, and the gravitational influence of each galaxy extends across enormous distances. As the two systems approach, those outer regions become part of the interaction, before the bright disks undergo their most dramatic changes. A spacecraft travelling between them would therefore pass not from one perfectly isolated island through complete emptiness into another, but through a broader environment shaped by both galaxies and the local group around them. Over billions of years, the entire neighbourhood would be reorganized. The present arrangement of the Milky Way Andromeda and their surrounding companions is temporary. Smaller galaxies may change orbits, become more strongly bound to one large system, or participate in the larger interaction. The dominant structures of the local group can merge and evolve into something that no longer resembles the two separate spiral galaxies visible in the current sky. From the perspective of deep time, the local group is not a finished object, it is a process. The present distance to Andromeda is one measurement taken during that process. This changing geometry does not weaken the central difficulty of the journey. A civilization considering departure now cannot treat the future approach of the galaxies as an engineering shortcut. The timescale of galactic interaction is enormously longer than any human planning horizon, and the spacecraft still has to solve propulsion, energy shielding, radiation repair, and deceleration. But the approach does remove one misleading assumption that 2.5 million light-years is an eternal separation. It is not. The number belongs to the present cosmic arrangement, and that arrangement is moving. There is something revealing in that fact. Human technology normally treats destinations as fixed, while vehicles move toward them. Intergalactic travel reverses that simplicity. The traveller moves. The destination moves, the origin moves, and the gravitational landscape between them evolves as well. A route to Andromeda is therefore not just a question of crossing a known distance. It is an interception between structures whose positions and forms change over immense spans of time. On shorter missions, the correction might be small enough to manage. On multi-million-year missions, it becomes part of the basic design. On billion-year scales, the entire meaning of departure and arrival begins to change, because the galaxies themselves are no longer separated in the way they are today. Andromeda is approaching, but the approach is not rescue. It does not turn a present intergalactic voyage into a feasible mission. Instead, it places the journey inside a larger truth about the local group. Nothing in it is permanently arranged. The distance that now demands millions of years from light will not remain exactly the same forever. The great galaxies are already changing one another's future through gravity long before their structures strongly overlap. Any imagined journey must therefore cross not only an immense gap, but a gap that belongs to a moving system. The destination is coming closer on a timescale so vast that by the time the geometry becomes fundamentally different, the civilization asking how to reach Andromeda may itself be only another ancient trace in the history of the Milky Way. The most difficult part of reaching Andromeda is not finding a single engine powerful enough to make the spacecraft fast. It is making every part of the mission survive the consequences of that speed, that distance, and that duration at the same time. Propulsion attracts attention because it offers the clearest image of progress. A faster ship appears to solve the journey, yet each increase in velocity changes several other problems at once. Energy requirements rise, acceleration becomes harder, deceleration becomes equally important, dust impacts become more destructive, gas particles become more energetic in the spacecraft frame, radiation protection grows more demanding, navigation requires greater precision, heat generated by propulsion and protection systems must be removed, structural mass increases as shielding and redundancy are added, and that additional mass demands still more energy. The challenge therefore behaves less like one technological barrier and more like a network of connected constraints. Improving one part of the mission often places heavier pressure on another. At low velocity, the environment is comparatively gentle, but the travel time becomes so long that technological survival loses practical meaning. At high velocity, the external journey becomes shorter and relativistic. Time dilation can reduce the duration experienced aboard, but the spacecraft enters a regime where every particle ahead carries more destructive potential. There is no simple speed at which all difficulties begin to decline together. The voyage becomes a balance among competing forms of impossibility. Energy is the first of those constraints because a massive spacecraft cannot be accelerated without paying for its motion. A vehicle intended to carry living organisms, heavy shielding repair systems, manufacturing equipment, power sources, and redundant infrastructure would be vastly more difficult to accelerate than a tiny probe. Reducing mass helps propulsion, but weakens protection and self-sufficiency. Increasing mass improves resilience, but makes relativistic travel more expensive. Even a propulsion method far beyond present chemical rockets would have to work within this conflict. Fusion could offer far greater energy density than chemical reactions, yet controlled fusion propulsion capable of pushing a large spacecraft toward relativistic velocity does not exist. Antimatter contains extraordinary potential energy, but producing, storing, and converting useful quantities into controlled thrust remains far beyond current capability. Beamed propulsion can move some of the energy source away from the spacecraft, but accelerating a substantial payload across extreme distances would require enormous infrastructure and still leave the question of braking at Andromeda. Every proposed route moves the burden rather than erasing it. Deceleration is especially easy to overlook because popular descriptions of high-speed travel often end at the moment the spacecraft reaches the destination. A vessel passing through Andromeda at a large fraction of light speed has not truly arrived. It has reached the region geometrically while remaining dynamically unable to stay there. Entering orbit around a star approaching a planetary system or conducting careful exploration requires shedding tremendous kinetic energy. Carrying the fuel for that maneuver makes the vehicle heavier throughout the entire crossing. Depending on an external braking system assumes infrastructure already exists at the destination. Using magnetic or sail-based methods would require conditions and technologies capable of removing vast amounts of momentum reliably. Arrival therefore reproduces the departure problem in reverse. The spacecraft must first acquire extreme motion and then surrender it without destroying itself. Between those two events lies the environment of the route. Intergalactic space is extremely thin, but it is not perfectly empty. At relativistic velocity, low density does not mean low risk. Hydrogen atoms, ions, dust grains, and background radiation all become more energetic in the spacecraft frame. A microscopic particle can release intense energy when struck at near light speed. Shielding must absorb, deflect, disperse, or survive those encounters repeatedly. Thick shielding increases mass. Active magnetic protection demands power. Forward detection systems must identify dangerous material early enough for avoidance or interception, but the faster the craft moves, the less time remains between detection and impact. The ship has created part of the hazard simply by moving quickly. Slowing down reduces that danger but restores the multi-million-year travel time that high velocity was meant to escape. Radiation adds a slower form of pressure. Cosmic rays and other energetic particles do not need to cause immediate destruction. Their effects accumulate through damage to biological tissue, electronics, insulation sensors, and structural materials. Over a short mission, shielding and redundancy can keep exposure within acceptable limits. Over immense spans, maintenance becomes unavoidable. Components must be replaced. Information must be checked for corruption. Power systems must be renewed. Repair machines must be capable of repairing one another. The spacecraft begins to resemble a self-maintaining technological ecosystem rather than a vehicle in the ordinary sense. If humans are aboard, the problem widens further into biology and culture. Air, water, nutrients, microorganisms, and waste streams must remain balanced. Populations must remain healthy. Knowledge of the ship must survive across generations. Social systems must continue functioning without external support. Across millions of years, even the word crew becomes difficult to preserve. The descendants of the original travellers would belong to a history so long that biological evolution and cultural transformation could become part of the mission itself. A robotic probe avoids many of these requirements, but not the fundamental demand for continuity. It still needs power, memory, navigation repair, and the ability to recognize and correct failure without help from Earth. Navigation adds another constraint because Andromeda is not a fixed picture at the end of the route. The galaxy visible from Earth is seen through light that left millions of years ago. The Milky Way moves, Andromeda moves. Stars inside both galaxies follow their own orbits. The local group evolves under gravity. A mission lasting millions of years cannot aim once and coast blindly toward an old image. It must observe, predict, correct, and eventually choose a precise destination inside a changing galaxy. The closer the spacecraft gets, the more current its information becomes, but arrival also demands greater precision and effective braking. The navigation problem therefore becomes sharper rather than disappearing near the end. All of these constraints explain why speculative ideas such as warp drives and wormholes remain attractive. They appear to attack the distance itself rather than merely improving the speed of a spacecraft moving conventionally through space. A warp drive concept in its most general theoretical form attempts to describe space-time geometries in which a region containing a spacecraft could be moved relative to distant locations without the craft locally exceeding the speed of light in the usual way. Wormholes are hypothetical connections between separated regions of space-time that could, in principle, create a shorter path than ordinary travel through the intervening distance. These ideas arise from legitimate mathematical possibilities explored within gravitational theory, but that does not make them available technologies. The existence of a mathematical solution is not the same as evidence that nature permits a stable, controllable engineering implementation. Proposed warp geometries have historically involved extreme physical requirements, including forms of energy distribution that are not known to be achievable at useful scales. Traversable wormholes face similarly profound questions involving stability, causality, exotic stress-energy conditions, and the absence of observational evidence that such structures can be created or maintained for transportation. Neither idea currently provides a practical route to Andromeda. They remain theoretical or speculative because the gap between an equation and a machine is enormous. This distinction is important. Modern physics does not provide a simple statement that every imaginable journey to Andromeda is absolutely forbidden under every future theory and every future technology. Science rarely earns certainty by declaring that all unknown possibilities have been exhausted. What can be stated much more securely is that known practical methods are nowhere close to solving the problem. No existing propulsion system can accelerate a crewed spacecraft to the required speeds. No demonstrated shielding system is designed for sustained relativistic travel across intergalactic distance. No human-built machine can maintain itself for geological time. No closed human ecosystem has been shown capable of surviving anything remotely comparable. No operational warp drive exists. No traversable wormhole is known. The gulf between possibility in principle and capability in practice is therefore immense. That is the real severity of the Andromeda journey. 2.5 million light-years is not simply a distance waiting for a faster engine. It is a distance that forces every weakness in transportation, energy, biology, materials, navigation, communication, and long-term autonomy to appear together. Solving propulsion alone would leave the ship exposed. Solving shielding alone would leave the journey too slow. Solving time dilation for the passengers would still allow millions of years to pass outside. Solving repair would still require power and raw materials. Solving navigation would still leave the energy of arrival. Each answer opens another demand. The journey is terrifying, not because known physics clearly forbids the destination, but because known physics allows the scale of the problem to be calculated with enough precision to reveal how far present capability falls short. Andromeda remains visible in the sky close by galactic standards and unreachable by any realistic human mission today. Its light crosses the gap without fuel shielding, repair, or fear. A spacecraft would have to do everything light does not and survive the consequences all the way to the other side. The distance to Andromeda remains difficult to hold in ordinary thought because every attempt to cross it brings time, energy, matter, and motion into the same quiet calculation. The galaxy appears near enough to be photographed from Earth, yet its light has already spent millions of years completing a journey that no massive spacecraft can match. Between departure and arrival lie not only empty kilometers, but changing stars, drifting galaxies, radiation dust, aging machinery, and the slow transformation of whatever civilization first chose to leave. Relativity can shorten the passage for travelers moving close to the speed of light, but it cannot keep the universe outside their vessel from moving forward. Advanced propulsion might one day reach speeds that now belong only to theory, yet every gain in velocity would demand new solutions for energy shielding, braking, and survival. Even the destination would continue changing while the ship approached it, gradually replacing the ancient Andromeda seen from Earth with a more current galaxy revealed along the route. None of this makes the journey meaningless. It gives the distance firmer edges. Andromeda is not unreachable because it is hidden behind a mysterious barrier. It is difficult because known physics allows the scale of the challenge to be understood with unusual clarity. The gap is measurable. The speed limit is measurable. The energy grows according to known principles. The hazards arise from ordinary matter encountered under extraordinary conditions. Beyond those facts remain possibilities that science has not yet turned into technology, and perhaps never will. For now, Andromeda continues its slow approach toward the Milky Way, while its ancient light crosses the darkness in the opposite direction. The journey between the galaxies remains open as a question immense in duration, severe in engineering, and patient enough to outlast almost every familiar measure of time,